The sun you see with your own eyes is already old news by the time it reaches you. Light takes about 8 minutes to cross the 93 million miles between the sun and Earth, so the glowing disk overhead right now is really a snapshot of what the sun looked like roughly 8 minutes ago. But that's the easy part of the story. The light actually escaping the sun's surface began its journey far deeper inside the star, and depending on how you count it, some of those photons have been fighting their way outward, bouncing between particles in the sun's dense interior, for anywhere from 10,000 to as long as 170,000 years, before finally breaking free into space. Every sunrise you've ever seen is powered by light that may be older than modern human civilization itself. And that's only what you can see. The human eye is tuned to a narrow sliver of the electromagnetic spectrum. And if that's the only window you use to study the sun, you miss almost everything interesting happening in its atmosphere. Since 2010, NASA's Solar Dynamics Observatory, a spacecraft built specifically to watch the sun in wavelengths far beyond what our eyes can register, has been capturing exactly that hidden activity, layer by layer, revealing a star that looks less like a static yellow ball and more like a churning, exploding, endlessly active engine. Start at the outer edge, the sun's faint, sprawling atmosphere known as the corona. Under ordinary visible light, the corona is essentially invisible, completely washed out by the overwhelming brightness of the sun's surface below it. The only time it becomes visible to the naked eye is during a total solar eclipse, when the moon briefly blocks the blinding photosphere and reveals a pale, wispy halo stretching outward into space. But observed in extreme ultraviolet light, at wavelengths corresponding to temperatures around 1,000,000 degrees Kelvin, the corona reveals itself in extraordinary detail, without needing to wait years for the next eclipse. It's in this same ultraviolet range that some of the sun's most violent behavior becomes visible. Solar flares, sudden intensely bright bursts of electromagnetic radiation, show up as brilliant flashes reaching temperatures near 20 million degrees Kelvin, triggered when the sun's tangled magnetic field lines cross, twist, and snap back into a new configuration, releasing enormous amounts of stored energy almost instantly. Elsewhere on the disk, you'll often spot the opposite kind of feature. Coronal holes, darker regions where the plasma is cooler, less dense, and magnetically open, meaning field lines here don't loop back down to the surface, but instead stream straight outward into space. These open channels let solar wind particles escape far more freely than usual, and when that particular stream happens to be aimed at Earth, it's often responsible for some of the most vivid aurora displays in our polar skies. Ultraviolet imaging also reveals towering arcs of plasma called prominences, sometimes visible rising directly from the surface, held aloft and shaped by the sun's own magnetic field. These structures can be genuinely enormous, large enough that Earth would look like a small marble sitting beside them, and while some form and collapse within a single day, others remain stable, suspended in the corona for months at a time. And in a detail that surprises most people the first time they hear it, the sun's atmosphere occasionally produces something that looks remarkably like rain, plasma that gets flung upward into the corona, cools and condenses there, and eventually falls back down toward the surface in glowing streams, still measuring in the millions of degrees even as it rains. For most of the space age, this coronal rain and these towering prominences could only really be studied in fine detail from orbit, because Earth's own atmosphere constantly shimmers and blurs anything a ground telescope tries to focus on, the same distortion that makes stars twinkle at night. That limitation finally broke in May 2025, when researchers from the National Solar Observatory and the New Jersey Institute of Technology unveiled a new system called Coronal Adaptive Optics, installed on the Good Solar Telescope at Big Bear Solar Observatory in California. The instrument measures the exact, constantly shifting distortion caused by Earth's atmosphere many times per second and cancels it out before the image is even recorded, effectively giving a ground-based telescope the steady, undistorted view normally reserved for spacecraft. The results, published in Nature Astronomy, produced the sharpest ground-based footage of the corona ever captured, an 18-minute time-lapse showing individual strands of solar plasma twisting, dancing, and responding to shifts in the magnetic field around them in real time, detail that had simply been unreachable from the ground before. It's a genuine reminder that one of the oldest, most continuously observed objects in the sky, studied for well over a century now, is still capable of revealing brand new visual secrets the moment we build a sharper set of eyes to look with. Not everything that builds up in the corona settles back down peacefully, though. Sometimes those same tangled magnetic structures don't just cool and fall, they snap violently outward, hurling billions of tons of charged plasma across the solar system in what's called a coronal mass ejection. Captured as a time-lapse in extreme ultraviolet light, you can watch one of these structures slowly build near the sun's edge before suddenly releasing, launching material outward at tremendous speed. A large enough eruption, if aimed squarely at Earth, carries enough energy to seriously disrupt satellites and power grids, which is exactly why solar monitoring missions like this one exist in the first place. How often these eruptions occur isn't random either. They rise and fall in step with the sun's roughly 11-year activity cycle, alternating between quieter stretches and periods of intense, frequent outbursts. Even switching between two different ultraviolet wavelengths, imaging the exact same region of the sun's corona at the same moment in time, can reveal completely different stories. One wavelength, tuned to cooler temperatures around 600,000 degrees, highlights calm, stable coronal loops. Another, tuned to roughly 2 million degrees, exposes far more energetic, actively churning regions in that same physical space. What looks like a single simple feature in one wavelength can turn out to be an intricate, layered chain of events once you look at it through a different slice of the spectrum entirely. Moving inward, past the bulk of the corona, sits an extremely thin, easily overlooked layer called the transition region, barely 60 miles thick, where the sun's temperature does something bizarre. It rockets upward, from around 8,000 degrees Kelvin to 500,000 degrees Kelvin, in a stretch of space thinner than most countries are wide. For comparison, molten lava erupting from an active volcano here on Earth typically reaches somewhere around 1,400 degrees Kelvin. Even the cooler end of the sun's transition region runs several times hotter than that lava, and the upper end of that same thin layer is well over 300 times hotter still. Beneath the transition region lies the chromosphere, the last layer of the sun's atmosphere before you reach the visible surface itself, roughly 1,000 miles thick and best observed in its own distinct ultraviolet wavelength. Here, some of the strangest and most delicate features of the entire sun come into view. Spicules, thin, grass-like jets of plasma that shoot upward from the surface at speeds exceeding 60 miles per second, fast enough to make them hundreds of times faster than the speed of sound here on Earth, some stretching upward for distances greater than the height of Mount Everest, only to form and vanish again within a matter of minutes. For decades, nobody could fully explain how these jets managed to break free of the sun's powerful magnetic grip at all. The answer finally came in 2017, when researchers building an unusually detailed model of the chromosphere realized that ordinary electrically neutral particles, one's earlier models, had simply left out because scientists assumed they had no meaningful effect, were actually providing the extra lift needed to launch charged plasma up and out into these spicules. Finally, descending past the chromosphere, you reach the photosphere, the sun's visible surface, the layer ordinary visible light telescopes are built to observe. From Earth, its edge looks crisp and sharply defined, but that's simply an illusion created by distance. The sun has no solid surface at all. Every part of it, at every depth we can measure, exists purely as plasma, sometimes called the fourth state of matter, a mix of ionized atoms and free electrons that behaves somewhat like a gas, but responds far more dramatically to electric and magnetic forces. Plasma, in fact, makes up the overwhelming majority, roughly 99.9%, of all the ordinary matter in the entire visible universe. The photosphere itself is only around 250 miles thick, and it happens to be the deepest layer of the sun that any instrument, using any wavelength of light, has ever been able to directly observe. Look closely at the photosphere and you'll often spot dark blotches called sunspots, patches that only appear dark by comparison to their blisteringly hot surroundings, caused by unusually strong, concentrated magnetic fields that suppress the normal churning heat transport happening just beneath the surface. Compare an ultraviolet image of a solar flare to a visible light image of sunspots taken around the same time, and a clear pattern emerges. Flares and sunspots consistently show up in the exact same locations, a direct visual confirmation that one phenomenon feeds directly into the other. Zoom in even further on the photosphere using ground-based visible light telescopes, and the surface reveals a completely different texture, a restless, ever-shifting mosaic of small, jagged-edged cells called granules, each one roughly 600 miles across, looking almost like cooling volcanic rock cracking apart in real time. Each granule is really just the visible cap of a much larger convection cell churning underneath, superheated plasma rising to the surface at its brighter center, spreading outward as it cools, and eventually sinking back down along the darker boundaries between granules in a cycle that echoes the same basic convection process, driving plate tectonics deep inside the Earth. Individually, a single granule survives for only about 20 minutes before dissolving and reforming, yet the fluid moving through it travels at genuinely supersonic speeds, generating shock waves across the surface as it does. And then the trail runs cold. Every wavelength of light scientists currently know how to capture, visible or otherwise, stops revealing new information once you pass the photosphere. Whatever lies beneath the final visible layer remains entirely inferred, rather than directly observed, reconstructed through physics and models, rather than actual images. It's a genuinely strange thing to sit with. The object providing essentially all of the energy that makes life on Earth possible, studied for centuries, still keeps its innermost layers completely hidden from direct view, no matter which part of the electromagnetic spectrum we point at it. But even within the layers we can see, one of the oldest open questions in solar physics may have just been answered. Why does the corona run so much hotter than the surface directly beneath it, sometimes by a factor of hundreds, when heat should logically get weaker the farther it travels from its source, not stronger? Physicists first proposed a possible answer back in the 1940s. A type of magnetic wave called a torsional Alfvén wave, a motion where the sun's magnetic field lines twist back and forth like a rope being wrung out, theoretically capable of carrying huge amounts of energy up from the surface and depositing it directly into the corona. For more than 80 years, nobody could actually see one happen. These waves were simply too small, too fast, and too faint for any existing telescope to resolve directly, leaving the idea as an elegant, unconfirmed theory sitting alongside several competing explanations. That changed in October 2025, when a research team using the Daniel K. Inouye Solar Telescope in Hawaii, currently the most powerful solar observatory ever built, captured the first direct evidence of exactly this kind of wave twisting through the corona. Using an instrument called cryo-NIRSP, cooled to extreme temperatures to detect faint infrared signals with unprecedented clarity, researchers finally resolved the small-scale torsional motion physicists had been searching for since before the sun's own composition was fully understood. According to the team, these upward-traveling twists appear to coexist with other wave types already known in the corona, and together they may finally explain how the sun manages to heat its outer atmosphere to temperatures that have puzzled scientists for the better part of a century. It's a rare kind of moment in science, a prediction made decades before the instruments needed to test it even existed, confirmed almost exactly as originally theorized, simply because someone eventually built a telescope patient and precise enough to catch it in the act. What using all these different wavelengths together really provides isn't just prettier pictures. It's the only method we currently have for turning an otherwise blinding, uniform disk of light into a layered, structured, genuinely three-dimensional story. One where flares, coronal holes, spicules, sunspots, and granules each occupy their own distinct piece of a much larger, continuously unfolding process. The sun looks calm and unchanging to the naked eye largely because our eyes were never built to see any of this. Everything described here has been happening continuously for billions of years, entirely invisible to humanity until the tools existed to finally look at the right wavelength, in the right place, at the right time.